first thank the organizer for inviting me to this very nice conference. So I'm going to talk, actually, the topic is very similar to the previous talk. It's about how can you make superconductivity better by making the system small. So then you see how this is related to the talk, the previous talk, but you will see how this is related. So first, let me start with some general motivation of this type of work. Superconductivity has been around for 100 years. And the reason for that is that it is sort of promising some sort of paradise in which you will get like room temperature superconductivity, and then humans won't have to work. And that has attracted many mavericks to the field. So these are guys that they are just by trial and error, intuition, they just try to get this type of room temperature superconductivity. And they were close, like with cuprates, or even magnesium diorite, which is a BCA superconductor, and more recently with iron-based superconductors. Also, that attracted the interest of theoreticians, and also some sort of hand-waving quantum phase transitions, mysterious quantum critical points. At the same time, also superconductivity has attracted people, what I call librarians. So they care about body materials like lead, like aluminum, like tin. Yes, they want really to understand what was going on. They didn't want to get room temperature superconductivity, but they just, along the last 50, 60 years, they make materials thinner, cleaner, smaller, with control. Because what they want to understand is that whether if you plug some theory like BCS, whether you could get really agreement between theory and experiment. And for that, it's critical just to have good control. So in this talk, actually, is one first try to in some sense, to unify these two communities. So in the last few years, there have been tries because they have a huge improvement in experiments, in experimental control. So now you have some, at least in some cases, there are different situations like when you have granular materials, when you have arrays, when you have interfaces, when you can use far from equilibrium dynamics in a very, very precise way. Now there are different ways in which you can try to enhance superconductivity with control. I mean, understanding what you are doing. So in this talk, I'm going to focus on arrays, but somehow the approach of this talk is opposite to the other talks that you start with some material that is very difficult to understand. And then you make some approximation. Here, in the end of the day, I'm going to start with the simplest thing that you can do in superconductivity. It's a single grain of aluminum, if you want to say. That is a perfect BCA superconductor. And then I'm going to make the system more difficult, but man-made. So I'm going to say, I'm going now to add this, and then I'm going to add that, and then I see how far I can go and still keep the analysis essentially analytical. So let me start why this is a good approach. So what you see here is a recent paper in which they study one atomic layer superconductivity in lead. What they found is that lead has a critical temperature of about 7 Kelvin. And they found the desired scale experiments that that even with a single atomic layer, they have perfectly BCS peaks. And then the gap is about also perfectly BCS, but still the critical temperature is instead of 7, it's 3. So that means that just by simply making a material smaller or thinner, you're not going to get higher superconductivity. Actually, you get a lower critical temperature. However, if you try more fancy materials, these are, for instance, papers. There are many papers like that, but there are this paper by Bosovic of 2008. He just put some bilayers of high-pitch superconductors, overdoped and underdoped superconductor. And what he found was something very, very funny. He found that in optimal doping, the critical temperature was about 40 for this type of materials. But then by coupling 2 layers, I think the optimal was metallic, overdoped, and optimal. He found critical temperature, they were about 40–50% higher. Of course, that's very interesting. So for in the last few years, people tried all the possible combination, all the possible trial and error to see whether maybe doing that you could get 100 or something like that. But as far as I know, this was unsuccessful. Of course, you ask me why he got this higher critical temperature. My answer is, I don't know. I could, of course, explain something, but the idea that I want to say is that maybe this is not the right approach. So these results, of course, are extremely interesting, but then if there is no follow-up, the same can be said about even more recent experiment with iron-based structures, with iron selenide. So essentially, they found that by just coupling iron selenide one single layer to a strontium titanate substrate, they found quite spectacular results. So they found that critical temperature, of course, the author are, let's say, optimistic. So they claim that the critical temperature is here. But even if it's here, still is an enhancement with respect to bulk iron selenide. And even more spectacular are these, that they just play with substrate, also with iron selenide films. They claim that these are STM experiments. So this is transport, but this is STM, so you have to take that with a grain of salt. They claim that they can enhance the critical temperature in the iron-based superconductor to maybe 70 or 80. But again, if you ask me why is that, so I don't know why is that. It's very interesting results. So what I want to do is like the opposite approach. You just start with the simplest model that you can imagine. You just take a single superconducting grain, nanograin. So then why you can see, for instance, enhancement of superconductivity in this single grain. And this, of course, is well known. This is not the first. So actually, this was the first we just think about that. Maybe was Parmenter. So just if you have a single grain of about, let's say, 10 nanometers, around the Fermi energy, you are going to have some. It might be that for some sizes you may have some accumulation of level around the Fermi energy, so you get an enhancement of density of states. And since that the speaker said, the last speaker, in BCS you get the gap depending on critical temperature is exponential with the coupling constant. So by increasing the density of state, you increase the coupling constant, and you increase critical temperature. So that is very easy. One very easy way to get superconductivity. So even though it was proposed in the 60s, it was not until recently that people, just with better computers, start to do numerical simulation, especially people here in this room. Peter, Shannon, Concrete, so they start to try different geometries just to see how is BCS when you just is confined in some different potential spheres, wires. And then what you can see here, this is actually from one of the papers of Peter's. And Shanenko. So you can see some, huge oscillation of the critical temperature as you just change slightly the size of the system. Then I studied in this business, just working with Boris and Schuller. So we just found some analytical way using periodic orbit theory to analytically found why you get this type of enhancement of superconductivity, both in chaotic, grains with no symmetry, but also in simple grains like cubic grains that also by doing just this type of, I'm not going to explain here, well, I'm going to explain a little bit later, you could get analytical results at least for a single grain. But still, this is sort of exercise. It's just solving the BCS gap equation in some geometry. So just it's very simple. Then a little bit later, so the group of Klaus Kerms and Gita Bosea in Stuttgart, they managed just to really, for the first time, produce this type of single isolated grains of about 10 nanometers. And then these are also the experimental results. So they found that by changing the size of the grain a little bit, you see a huge fluctuation of in that case of the gap, 14. And then what it was surprising is that just by using a plain, simple model of BCS with no free parameters, just plugging numbers from textbook, you could get a very good agreement between theory and experiment. So this, I participated in this work, so it was published in 2010. But still, this is just the simplest thing that you can do. Single grains, zero-dimensional, so no space, no time dependence of the gap, and BCS. Of course, if you want to go beyond one grain, you need to understand correction to BCS. And actually also this experiment, this provides some deviation from BCS. For small grains, this is just temperature. So they saw this is just BCS, and they saw some deviation from BCS. This is what you know from your class in statistical mechanics. Your teacher always tells you, phase transition only occur in infinite systems. But you said, what? But this is a proof that, of course, there are many others, that when you go the system is small, there is not really sharp phase transition, there is only crossover. What we did also after this is just try to understand how are these deviation. For these are, again, zero-dimensional models, so you don't have many of the things that have been discussed here. The correction to BCS here are even easier because, for instance, for thermal fluctuation, you can do a static path approach in the path integral, and then you can do exactly when you don't have time dependence. And then you can put on top of this thermal fluctuation, you can put quantum fluctuation either by solving exact BCS gap equations or by doing some sort of random phase approximation. the outcome of this is that also without using any free parameters, still you can describe experimental data, because this is very simple. These are extremely simple systems. And this is what we do here. So this is just this black line is this is just a gap as a function of size. This black line is without cheating. I mean, just plugging numbers from textbooks. And this is just assuming that, of course, when the system becomes very small, actually it's not true that it's BCS, because you may have another correction, or at least the coupling constant. This is just by doing some interpolation of the coupling constant, effective coupling constant, that depends on system size, that is reasonable. But what is interesting is that even without doing anything, still the behavior between theory and experiment with no free parameters is quite good. But you can do even better, because even till a few years ago, for single zero-dimensional grains, it was not possible to combine thermal fluctuation and quantum fluctuations. Because there was some problem, people tried, and they found some infinite in the path integral. And then we found that all these problems of just to compute what are the interplay between thermal and quantum fluctuations, they are due to the fact that you have to remove these zero modes. So when you have the path integral, you have some modes that cause no energy. Of course, these are like the usual modes that you know that when you have system which is not when the system is not zero-dimensional, they give you two Boston mode. But here is they don't have dynamics. So we found that just by removing this type of zero modes, even in a zero-dimensional, you can get some expression that combine thermal and quantum fluctuation. So the idea, again, this part, the first part of the talk, is just to say that now we understand both experimentally and analytically one single grain, the simplest case. But now, of course, I have said before, enhancement of superconductivity, larger gap, but really if you have a single grain, you just Heisenberg principle, you cannot have any type of phase coherence. So the question is, what happens if you put one of these nanograins together, right? Are you going to have some sort of enhancement of superconductivity or not? Actually, Nadia Mason in 2011 was the first just to experimentally study this type of grains, but in his setting, the size of the grain is about 100 nanometers. So that means that all these effects that I want to study, like size effect, are not visible in this type of physics. Still, you have some interesting physics. You can see some sort of transition as you move the distance between these grains. But so what I want to tell you in this talk is what happens when you do this type of grains. But these grains, now they are nanograins of the order of 10 nanometers. So what we said before is that something like that has been tried in the literature from like the 70s. And at least for aluminum, what they found is that if you take this type of array, this is a sort of disordered array, with a grain size of about 5 nanometers, they found, and this is just the resistivity, they found that a huge enhancement of the critical temperature. So they found that even though for aluminum the critical temperature is 1 Kelvin, they found critical temperature of about 2.5 Kelvins. And this is known actually for all experimentalists you ask, that is known that granular aluminum, the critical temperature is higher. So the motivation for that actually, for this work, was try to, using a setting like that, which is still experimental, is not possible, for the sizes that we are interested, whether we can see an enhancement of superconductivity. So let me explain why, what we want, when you engineer, you want to do something that is realistic. So that means that what we want to do is we want to study this type of array in which these grains, they are distributed according to some Gaussian distribution, with sizes of, let's say, 10 nanometers. And we know that some of these grains, they are going to have a higher critical temperature than the bulk, and others, they are going to have a lower critical temperature than the bulk, because of this size effect. So because of this size effect, if the Fermi energy, there are many states, then the critical temperature is going to be higher. So the game here is going to be, the total critical temperature of the array is going to be higher or lower than the one of the bulk material. And so, just in some pictorial view. So let's say if we are very close to very high, for temperatures very high than the bulk critical temperature, so we expect that still some grains, they might be superconducting, because it could be that by chance. I mean, there is a high concentration of levels, but most of them will not. So that means that it's not possible to see any percolation or something like that. Now, what we want to answer really is that if we have a temperature which is even higher than the bulk, still maybe there is some percolative path, or maybe which I mean, you can have some percolative path in a way that you may have some critical temperature of the total array, which is higher than the bulk one. So, of course, if you go then to lower temperature, eventually all of them they are going to become superconducting. So, let me tell you then all the ingredients of the model. Again, here the motivation is just you put different ingredients because first it's more motivated by experiments. You do, of course, what you can do. So we want to do 3D. So why we want to do 3D? We want to avoid DKH V6 and we would prefer to do BCS. So we do 3D, which actually means that we don't do 2D. So we can do 2D plus something else, but we don't want to do strictly 2D. We want to do nanospheres. So what is the shape of this grain? So we want to study. So this is because experimentally, this is the simplest thing to do. Also, are the ones that have largest size effect because you have degeneracy. So they expect that you can have big fluctuation of the density of states. Of course, we assume that it's clean because these are very small, so the mean free path is going to be much larger. And then for free, in the models of just conjunction, we can include quasi-particle tunneling and charging effects. And also, we want to study another parameter we have is how we pack the grains. Because in principle, experimentally, provided that you are able to do this type of arrays, you can do any type of packing. And the size, these are given by the experiment. So typically you talk to experimentalists, they tell you that to do 5 nanometers, for instance, is fine, or 6 or 7 nanometers usually is fine. And this is the usual standard deviation that you can get experimentally with the current technique. Then these two, now the next step, I want to explain what kind of techniques I'm going to use to describe this, because the motivation here is to do something which is analytical. So for the single grain, we are going to use BCS theory. So that means that the mean level spacing is going to be much larger. So that means that we cannot do very, very small grains. Also, we want to do some semi-classical approach. This is periodic orbit theory that was developed in the 70s and then was employed in the context of quantum chaos. So we need this type of condition. We should tell you that we cannot say anything for very small grains, but still for very small grains, like 2, 1 nanometers, we don't do BCS. Then the next step is this is for single grains, but we have to make this grain open, because when we have this size effect, by coupling the grains, this size effect they are going to be weaker, because the system is going to be open. So then that means that we need to include tunneling between grains in our model, that we know how to do in the context of periodic orbit theory, just by using some cutoff. And then this is just for single grains, but now we need to study the array. Of course, the array can be studied usually just by percolation. This is one simple thing to do. And the other is just to do some mean field that includes charging effects to see whether the transition is induced by percolation or by phase fluctuations. So let me, then these two transparency are very technical, just to make sure that you think that I'm able also to write formulas. So essentially when you do periodic orbit theory, you can express the density of states in terms of classical periodic orbit of the system. So if you have a sphere, these are just the difficult expressions. The interesting here is that by making the grain open, in this type of formalism, you just have to include some cutoff, which depend essentially of the tunneling rates, which depend on the normal resistance of the material. So that means that with this simple expression, then you can plug this here in the BCS gap equation, and you can solve this analytically as a function of, in terms of the small parameter 1 over KFL, and then still you can get analytical results. Still, by making the grain open, you are making your size effect smaller. So that means that we expect that the deviation from deviation from the bulk limit, they are going to be smaller. So this is with respect to single grain, technically how we do it. Now, the array, to study the array, we use a simple, in 3D we can do mean field, and then we use the usual model in the literature for Josephson array. So that means you have a term, charging effects, phase fluctuation, then you have the hopping term, phases. And that now what is different here is that each of these guys has a different gap, because each grain has a different gap. Okay? And also we can include for free quasi-particle tunneling, because quasi-particle tunneling is going, in the end of the day, once you do these green functions, you expand and you are careful, this just renormalize the value of the capacitance that you are using here. In the end of the day, you can do a mean field in 3D, and then you end up with some mean field equation that I'm not going to discuss here. The only thing I'm going to discuss here is that what we do to compute critical temperature is to make the following assumption. But it's to assume that when you are, at least when you have percolation, the critical cluster is going to be about, the dimensionality is going to be about 2.25 or something like that. So that means that in 3D we are safe, because even the critical cluster, the dimensionality is larger than 2. So we don't have to worry about vortices or about something like that. So we only have just to solve this, and then we can assume that we can, all this is intrinsically inhomogeneous, right? But we can make an approximation that close to the critical cluster, we can just replace that by something homogeneous by rescaling the value of the numbers of nearest neighbors. And then we solve this mean field equation. Of course, numerically, but this is something very simple.
Sorry. The charging energy is the one of the electrons.
Yeah, I mean it's the one which is 4 pi epsilon naught r. So it's no, this is just the capacitor and the classical. This is some classical. I'm not discussing Coulomb interaction.
It has to do with the array. So what is in between the grains? So it's nothing to do with the properties of each grain.
I mean, it has to do with the properties. No, I think it's the other one. Because it's 4 pi epsilon naught r. So it's
the one of
the charging energy of the single
grain. Yeah, you have to include another term here. Actually, well, you should put case a matrix. This is the diagonal. You should put a matrix. Of course, this also is an you could also do that. Okay, so just let me show you the results. Again, so you have percolation and phase fluctuations. You have to compute the critical temperature in both cases, and whatever is lower is the one that you take. And here, for instance, we change the distribution of the size of the grains. So it's Gaussian, and this is just the standard deviation. We take a value of 5 nanometers, and these are coupling constant 25. Let's say this could be tin or aluminum, but we are not discussing materials at the moment. So what you see here is that for typical values, you get an enhancement as you increase the resistance of the material. By increasing the resistance, you are making the size effect stronger, because the grains, they are more isolated. So then you can see enhancement, which are about, for these values, are about like 200% or something like that. What is important is that you have to go to extremely low, extremely narrow distribution to see some big difference. And this is not, nowadays, nobody knows how to do this type of narrow distribution experimentally. Then let's say that we change the coupling constant, keeping typical values for the size and for the standard deviation. Then we see something which is what we expect. So if we work with very weak coupling constant, the enhancement is bigger. Why? Because small changes in the density of states induce big changes in the gas, in BCS. So that means is that you get better results. The most boring is your material, if you want to see it like that. Okay? And also, this is actually was something, though expected, was quite a surprise, is that now we keep coupling constant size and we change the packing. So if we go for cubic, PCC, FCC, and then we find that for the one that I think is FCC that has a largest coordination number, we get actually a huge enhancement. So packing is the most important maybe ingredient. So if you manage to pack your grains, in the most efficient way, you can get an enhancement of about 3 times, or maybe around 3 times. Now, the question is
sorry, but the different lattices are with fixing what?
No, this is fixing. We fixing these 3 parameters. Of course, we could, but these are all these are. Of course, I don't want to show you 20 transparency.
But the nearest neighbor distance is the same. In all
The
nearest neighbor is fixed.
Yeah.
Not the lattice parameter.
No. We want to change the connectivity.
Okay.
And then the question again is the origin just percolation? Because we compute the 2, but we didn't show that. Or just because phase dynamics. We introduce some charging effects. We put this charging effect like 4 pi epsilon naught r, whatever it is. And then also we show that these are more or less stable, but still on physical ground is induced by percolation or is induced by phase dynamics. And this is the answer also for some typical value parameters. So it means that first is control, so this is percolation, and this is phase fluctuation. So that's also is sort of not very surprising. So that means that when the resistance is very low, so the grains actually are almost a big grain. So that means that phase fluctuation, they are not going to be important. So it must be by percolation. The transition is induced by percolation. As you increase the resistance, then the grains, they become completely isolated or mostly isolated. Then you expect a transition induced by phase fluctuations, and this is what you see. And then still, all what I said for this model is just for this type of array. But this type of arrays, now people can do that like 50 nanometers of size. So to see what the physics that I'm describing, you should do about 5 nanometers. I still, this is for lithographic techniques that seems difficult to do at the moment. Still, these are like what people can do now. I mean, of course, can do more than people did 66, but still, it's something like a sputtering or something that you don't have control. Still, I could describe this model. I just put out some random hoppings in my model. And this, without doing any calculation, what it's going to do is to make this effect. Still, you are going to see similar physics, but more modest result, because by making your coupling random, it's more difficult to enhance, to find the optimal path. So that means that if we do experiment with the current technology, it's possible to get some enhancement, but not as strong as the one I'm describing. Though this type of things, in principle, it's possible to do. It's nothing against to do that in the coming years. So yes, let me finish, and then thank you.
So the idea of the optimal path is clear. So you enhance TC because somehow you are so lucky that you make percolation along the gas with IOTC.
Yeah.
But then when you plot the curve as a function of the resistance,
Yes.
So why you have an optimal resistance if you want to get the optimal TC?
Well, but the optimal resistance depends actually on the capacitance that I put by hand.
Yeah, so it's the capacitance.
Yeah.
So it's, but
The capacity.
what is special in one value or the other? Because one would say that...
I don't have a clear... Okay, you have these two things which are completely different physics. And now you just try, and then you see, of course, if I now put my capacitance 10 times bigger, I'm going to see this transition from percolation to the left. Or the opposite, if I put it smaller, I go to the right. I don't have a... Still, maybe it's possible just looking at the equation to find some sort of relation between critical capacitance and percolation, but I don't know some quantitative...
So the distribution of the size was Gaussian,
Yeah.
but the distribution of the local TC is not Gaussian,
No.
Because you said that you
No,
have...
that's a good question. No, it's not Gaussian. Actually, it has like long tails. We didn't do
did
that.
you try to extract your...
No, since we have analytical results for each grain, we didn't do it. But I checked that it has long tails.
Okay.
Yeah.
Okay, thanks.